All right, welcome to the third and final part of today's lecture where we're going to be going over different types of collisions we'll be dealing with in this class. So first, let's talk about what is referred to as the perfectly inelastic collision. So a perfectly inelastic collision is where it's where whatever number of objects we have stick together. 2, 3, 5, whatever number we have, they're all moving independently. They come, they hit each other, and then they all move together afterwards. So here we have a example of what this looks like. So we have ball 1 and ball 2 moving together. They then collide together and start moving together afterwards. So this is kind of similar to how we dealt with the child and the boat in the previous video, where they moved together, meaning they had some common final velocity. Now in the case of the child, they were inside the boat. They didn't stick to it or run at it and get stuck. Slightly different, but how we treated the masses and the velocity was the same. They moved together. The other type of collision we're going to be dealing with is the elastic collision. So perfectly elastic collisions are ones in which mechanical energy is going to be conserved. So these are the nice ideal cases, and instead of referring to them as perfectly elastic collisions, typically we just refer to it as an elastic collision. So when we had the two objects sticking together, it was perfectly inelastic. It was perfect in a different way where the two objects moved together. The elastic collision is one where mechanical energy is going to be conserved, and the other type of collision, the one that we would have in a day-to-day situation, would probably be referred to as the inelastic collision, where you would have things like friction or mechanical energy not being conserved. But that's not one we are going to be dealing with in this class. We're only going to be dealing with elastic, where mechanical energy will be conserved, or with perfectly inelastic, where the two objects stick together. So here we have two objects. We have object 1 coming and colliding with object 2, which is starting as being stationary. And the reason this is nice is we're going to get some unique equations from going through and doing this math. So it has some value of kinetic energy. We then have a collision happening, and then we have the after situation where, in this particular case, both objects are moving to the right, and that means that our final velocity, our final kinetic energy is going to be equal to initial kinetic energy. So mechanical energy does talk about elastic and gravitational potential energy as well. Here, because we're only moving on X, we're assuming we have a nice flat surface, so gravitational potential energy doesn't matter. It's just going to be 0 for everything. In the case of elastic potential energy, it's going to be effective during this part of the collision, but not in the before or the after case, so that value would be equal to 0 as well, meaning we're only dealing with kinetic energy. We're looking at the before and after cases of the collision. So here we have what would be the conservation of momentum before, as written out by the textbook. So it's got all the subscripts you could ever possibly imagine. And we then have the conservation of energy for the after case as well. So we have, the before and after case, it has to be conserved because we have an elastic collision. So you'll notice that we've matched the velocity notation for both of these because why make things simpler when we can make them more complex? For some reason is the motto of momentum. So using algebra, working through it, we can get two unique equations. So again, we're skipping the proof. If you want to see this, check out chapter 11, section 3. We get these two equations here. So to find the final velocity in the x direction for object 1, we take the mass of object 1 minus the mass of object 2 divided by the mass of object 1 plus the mass of object 2 times the initial velocity of object 1. To find the final velocity of object 2, we'd have 2 times the mass of object 1 divided by mass of object 1 plus mass of object 2 times the initial velocity of object 1 squared, or object 1, not just squared. So these equations are really nice because we can find information right after the collision, right? We can find the final velocity of object 1 and object 2. However, it comes with a lot of conditions. We have to have an elastic collision, one in which the kinetic energy is conserved. We must have the situation where ball 2 is initially at rest. Now, if for some reason ball 2 is the moving one and ball 1 is at rest, you can just flip which one's considered 1 and 2. That is a valid thing to do because you're the one choosing what's what. So this is helpful, but it's not quite the most helpful that we can have. So if you wanted to know what the equations look like when both are moving, it looks like this. So we just have another term that looks very similar to the term that the other equation has. So I'm just showing you these equations to look at. So both with this slide and the last slide's equations, I do not recommend always starting with them. It's not always going to be beneficial, especially when we start looking into multiple dimensions. Things are going to get a little bit weird and we're not going to need them. We're going to do an example using not this form of the equation, but the other one. We're going to do an example with it. However, I want to make it clear that it is not always going to be the best place to start looking at our questions. Because again, we have to have an object at rest and kinetic energy has to be conserved. The second we start having things with an angle, so as soon as we start dealing with 2 dimensions, this is going to get a lot harder to use because it turns out in a lot of situations for 2D, we're not always moving in 2 dimensions to start with. So these equations are not always what you should look at first. In the case of one-dimensional elastic collisions where one object is at rest, they are fine. But as soon as we get to 2 dimensions, or as soon as something is not at rest, I mean, if it's not at rest, we can use this version, but we need to make sure we have a situation where we can use these. The textbook says, oh, don't memorize these, don't expect to start at them, and then does a bunch of examples where you should start at these. But it's only for this particular section. So here we have a model for the collisions. So here we have a model for the perfectly inelastic collision where the 2 objects stick together. And then here we have the perfectly elastic collision where, again, this is for 1 dimension, kinetic energy conserved, what these equations happen to look like. Here it talks about how to make it so that you can do a transformation to pretend the other object is at rest. We're not touching the Galilean transformation in this class. So let's just ignore the fact that that exists. So yeah. So again, these are valid starting equations if one object is at rest, we have perfectly elastic collisions, and we are moving in 1 dimension. So let's do an example using the perfectly elastic collision case. So what I'd like you to do is pause the video, draw a picture, and go through and solve this question. Okay, so let's draw our picture. So chose white on accident. So because we are dealing with the one-dimensional case here, we know that our objects are going to be moving in 1D. So they're going to, marble 1 is moving towards marble 2. They are going to collide, and then we don't know any information about 1 and 2 afterwards. So let's just pretend they're both moving to the right. It's possible when we do the math we find a negative sign pops up. That would just mean that one of the objects, probably 1, would be moving to the left. So we have some information given. So we have mass 1 is 50 grams or 0.050 kilograms. Mass 2 is 20 grams, 0.020 kilograms. And we know the initial speed of 1 is going to be equal to 2 meters per second. So when I'm going through and I'm going to set up this equation, I don't know the final velocity value of either of my two marbles. However, I know the initial value for 1 and I know the masses, so I'm going to be able to use those equations that are derived from the conservation of momentum and from the conservation of kinetic energy and algebraically combined together. I'm going to start with those because this is a situation I can use them. Again, when we start looking at different situations, can't use those equations. So let's look at how, so we have, because I'm only moving in x, I'm not even going to include the x here. So I'm just going to drop the x. I'm dropping the x because I'm only moving in x. Again, I'm going to drop the 1 or the initial because, well, I'm using a different notation for my final. I'm using this little tick mark, this prime notation, to indicate it is changed, which means I can get rid of any I for the initial value. So I can use this equation to solve for the final velocity of 2, and the other equation, mass 1 minus mass 2, divided by the two masses added together. I can use this equation on the right to solve for the final velocity of marble 1. So if we look at these equations without plugging in any numbers, there is no way, if our initial velocity for object 1, I set it up to be positive to the right. That means there's no way that marble 2 is going to be moving to the left. All my masses are positive, so I'll have a positive divided by a positive times a positive. That means that no matter what, marble 2 is moving to the right. If I look at my equation for the final velocity of marble 1, I have marble 1 minus marble 2. So if marble 2 has a larger mass than marble 1, well, that would mean that it would be a negative value divided by a positive value, in this case times a positive value, which would mean that I'd have a negative velocity, meaning I'd be moving to the left. So by knowing the relationship between the masses, using this equation here, we'd be able to find the direction of marble 1. So let's go ahead and let's focus on calculating the value for marble 2. So I'm going to 2 times 0.05 kilograms divided by 0.05 kilograms plus 0.02 kilograms times 2 meters per second. Taking that and plugging it in, I got 2.857 meters per second. Or if I wanted to be picky with sig figs, I was given 2 in this case, 2.9 meters per second. For marble 1 over here, I'm going to have 0.05 kilograms minus 0.02 kilograms divided by the 2 added together. Probably should have given myself some more space. All right, times 2 meters per second. When I took this and plugged it in, I got 0.8571 meters per second, or that my final velocity for object 1 is 0.86 meters per second. So we can check if these answers make sense. Because just looking at it, it seems a little wild that somehow Marble 2 is moving faster than Marble 1 ever was. Right? We started at 2 meters per second, now we're going 2.9 meters per second. So let's take these numbers and let's plug them into the conservation of momentum to see if this works out. So if we have the initial conservation of momentum, we'd have mass 1 initial velocity of 1 is equal to mass 1 final velocity of 1 plus mass 2 final velocity of 2. So we were given all of the initial information. So we had 0.05 kilograms times 0.2, so 0.01 kilograms times meter per second. So let's try our values for afterwards. So I have 0.05 kilograms. I'm going to use the rounded ones. Technically, we should use more sig figs, but this is just to check and make sure we're right in the correct ballpark. So we're not going to be super picky. So I have my 0.86 that I got before, my 2.9 that I have for after for ball 2. So we need to make sure that we plug this in correctly, because I'm going to be honest, I did it wrong the first couple of times. What I end up getting is 0. Wait, did I plug in? Sorry, I added an extra 0 here. This should just be 0.1. I got 101 kilograms times meters per second. These are approximately the same. If I rounded to the 2 sig figs I would need for my solution, they'd be identical. So this indicates that my solutions are correct. That the speeds that I've gotten for, Marble 1 and Marble 2 afterwards are right. So even though my initial velocity for Marble 1 was 2, the difference in mass that Marble 2 has compared to Marble 1 results in a different value for my velocity. So it's possible when you have a smaller object for it to move faster than the initial object. So as soon as you get a larger value, that does not mean you're wrong. Check your masses. If you're using this method, you can go through and use the conservation of momentum to check and make sure you have roughly the correct value that you would expect to get when it comes to comparing the final momentum to the initial momentum. All right, so that's going to wrap it up for today's lecture. If you have any questions, please let me know. If you haven't taken the lecture quiz, please be sure to do so.